Today we're going to look at the periodic table and see how you can use where the elements are on the table to predict their oxidation states or their possible charges when they are in a compound. And then we're going to use those possible charges to help us with writing formulas and then later on naming compounds. So if you look at this table, you should be able to see that you have various columns that are going down. These are called groups or families because one thing they have in common is the same number of valence or outer shell electrons. So if I'm looking, for example, in this first column with hydrogen, lithium, sodium, and so forth, these all have one valence electron. There's a rule that's called the octet rule that basically says that for most elements, except some of the little small ones, they want to have 8 valence electrons in their outer energy level to be most stable, so that when they become a compound, that's their goal, is to get that octet. Now, hydrogen, lithium, beryllium, boron, and helium don't follow that rule because they're just very small. But anything carbon or larger, when they get put in a compound, they're trying to satisfy the octet rule. Just keep in mind there's always exceptions, so we'll be talking about some elements that break that rule as well because they want to have more than 8 in their outer energy level. But we're not going to worry about that at this point. So if I'm looking at this first column, these all have 1 valence electron. The second column has 2 valence electrons. And then we're going to skip all these in the middle for the time being. These over here have 3 valence electrons, 4, 5, 6, 7, 8 with the exception of helium. Now if you'll notice when you're looking at these, you can actually look at these second numbers to figure out their valence electrons. So boron has 3, so it's in column 13. Carbon has 4, column 14. Nitrogen has 5 in column 15 and so forth. Okay? So that's a good indicator. Now this is one way you can number the table. This is the aromatic way. There's also a way you can do it with Roman numerals. So typically when we're looking at these, if we're looking at this column, it would be the group 1A column. The second column is typically the group 2A column. These in the middle are going to form in what are called the B columns, and we'll get to those another time. And then if we look at these, this will be the group 3A. Oops. This will be the group 4A. Nitrogen is the group 5A. Oxygen is the group 6A. Fluorine is the group 7A. And then this column is the group 8A. If you number them this way, then all you have to do is look at the Roman numeral to get their valence number of electrons. Now, if these are trying to get the octet, then if I have 1 valence electron in this column for all these elements, then they either want to try to lose 1 or try to gain 7. So it's going to be easier for them to lose 1 than to gain 7. So if you lose an electron, but you keep your proton numbers the same, then that's going to make everything in this column have a +1 charge. The only exception to that one is hydrogen, because it can also have a -1 charge depending on if it's with a metal or a metalloid. And we'll look at some examples of that in the future. The second column has 2 valence electrons, so it can either try to lose 2 or gain 6, so it tends to lose the 2, which means that these are going to have a +2 charge. Now these 2 columns are always going to have those charges. So that helps it when you're naming some of these a little bit later on to know that. If you go over here to the group 3A, that has 3 valence electrons, so they can either lose 3 or gain 5. So again, most of them are going to want to lose the 3. Now this is when it gets a little hairy because you have this little stair step that separates these columns right here. This separates the nonmetals over here from the metals over here, and basically anything that's touching this entire line, and again, of course, there's an exception, with the exception of aluminum, is what we refer to as a metalloid. Or some books will call them semimetals. So typically, if you have something that is below the line, it's going to act more like a metal because it's near the metal side. If it's above the line, it's going to act more like a nonmetal. Metals have positive charges. Nonmetals commonly have negative charges. There are exceptions. Just keep that in mind. All right, so if we're looking then at our column 4A, which is the carbon column, it's going to be one of those that's kind of sitting on the fence. So it can either be plus or minus 4. Now this column has a lot of variation in this, but if you had to guess, that would be a good way to look at it. Then if I looked at my nitrogen row, has 5, so it can either gain 3 or lose 5. So here's where the gaining starts. So these are actually going to gain 3. So this column typically has a minus 3, and that's going to be for those elements that are typically on the non-metal side of this stair step. For these down here that are on the metal side, they can usually take on a positive 3 charge, but they could have multiple charges. So that's one thing we'll look at in just a minute. And then our oxygen is 6A, so it's going to want to lose 2 instead of trying to gain 6. So these are typically minus 2. Again, these metals or metalloids can have positive charges. Your fluorine has 7, so it's going to want to lose 1. And then, of course, these are the noble gases. These are already in their most stable conformation, so they don't have an oxidation state. Now, for anything that's in this middle area here, these are called transition metals, and these down here are called rare earth metals. They actually come out of the table where this little blue mark is, so you can see that's 56, and then you start here with 57 and go across. All right, 57 and 57 and 89 are typically back up on the chart, but they're just kind of showing you, they're pulling them down here. Anyway, any metal that's in here or here, with a couple of exceptions, have multiple possibilities for the oxidation numbers. And so this is one of the things that you'll be looking at when you're naming ionic compounds, is you have to use a Roman numeral in the name to indicate what charge it might actually have. The exceptions for this one are going to be silver, which is always plus 1, zinc, which is always plus 2, and cadmium, which is always plus 2. And then aluminum up here is always plus 3. So if you can learn those 4 elements, silver plus 1, zinc plus 2, cadmium plus 2, aluminum plus 3, and then these 2 columns, then those are the elements that do not need Roman numerals because we know their charge, that we know their oxidation state. For any other metal, we don't know for sure its oxidation state because they could have multiple ones. Therefore, we have to indicate that charge in the name, and we do that by using Roman numerals, which I'll show you shortly.